Hello viewers, welcome to Bhadra Academy. Once again we are here with the CUET undergraduate program video, where today we'll discuss about the cells that are connected in series and parallel, right? And also this is our phone number where you can contact us for the details about the CUET undergraduate program courses, the fee structure, the classes and all the details. So let's begin with our topic of series and parallel connection of the cells, right? So series and parallel connection of the cells. First we'll take up the series connection of the cells, and here you can see that in the series connection of the cells are connected in the sequence wise, right, where the positive terminal of the cell is connected to the next negative terminal of the cell, and this wise the connection is known as the series connection of the cells. In the circuit diagram you can see this is the circuit diagram where you can see the polarity is in this way, right? And therefore if we take out the equivalent EMF of this circuit, then we will have certain derivations. Here we can see that a set of batteries is said to be connected in series when the positive terminal of one cell is connected to the negative terminal of the succeeding cell. So that is what we have seen here. Here the cells are connected from end to end such that the same amount of current passes through each and every cell of the circuit. So here the very important point is that the same amount of current will pass through each cell. Okay, so the current will not be divided, but the EMF will be divided. So every cell will have its own EMF, and combinedly we will have an equivalent EMF of the circuit. Okay, so the overall EMF of the battery is again the algebraic sum of the individual EMF all the cells connected in series, and therefore we have this equation, that is for the two cell circuit we are giving here that EMF equivalent is the summation of algebraic sum of the E1 and E2, but we also know that each cell has internal resistance, so therefore the equivalent internal resistance of the circuit is also the internal resistance of battery 1 and battery 2, that is R1 plus R2. And if it is a number of cells, so then we will have the equivalent EMF, that is the algebraic sum of all the number of cells E1 to En. Okay, so this is the circuit discussion about the series connection. And for the parallel connection, you can see again the batteries are connected in parallel. So here also you can see that the current that is flowing will be divided again and will be the summation of all the currents that is flowing in the circuit, but the voltage here will remain the same. Okay, so in earlier circuit we have seen that the current was remaining same, but here the total current will be the individual current, that is I1 plus I2, and the total current will be I. Okay, so here also we can see that in the parallel connection a set of batteries is said to be connected in parallel when the positive terminals are connected together and the similarly negative terminals are connected together. So these combinations are referred as parallel batteries. Also the cells are connected in similar terminals such that the same voltage is across every cell in the circuit, and the overall current in the battery is the algebraic sum of individual currents connected in the parallel. So therefore again with the current equation will come, that is the I equivalent, the total I, that is the current given by battery 1 I1 and current given by battery 2, that is I2. So this is the equation. And the internal resistance, right, since it is parallel connection, so we know that parallel connection equation is given by 1 by R equivalent plus 1 is equal to 1 by R1 plus 1 by R2. And finally we can say that if for an n number of cells, so I equivalent will be I1 I2 and till In, right? So this was the discussion about series and parallel connection of the batteries. I hope that you have understood. Thank you so much.